So now I'm going to introduce the metric space axioms, and the metric space axioms are the ones that permit me to talk about distance between points. And we will eventually encounter other measurement axioms that make precise what we talk about when we talk about measurements of angles, for instance, or measurements of areas. But these axioms will talk about the distance between any 2 points. Now, it's easy and somewhat helpful to phrase the metric space axioms in terms of a function, right? You put in 2 points and you get out the distance between them. So that's the notion of a function, and if I just kind of constrain or describe the properties of a specific distance function, a distance metric is what it's called, then I can say that a metric space is any space where you have a distance metric. So in any case, the important point is that this distance metric for any 2 points gives you a real number, right? It's, the real numbers are just kind of the familiar numbers like pi and 1, 2, 3, and all the numbers that you frequently have encountered in school, but they don't include, if you've ever encountered complex numbers like the number I, that's not included, but everything else is. So a distance function has to give you a real number, of course. The distance between some 2 points could be 1 or 2 or pi or whatever. Another property is that any 2 points must have a distance between them, right? You couldn't have some 2 points where there's no such thing as a distance between them. That doesn't make any sense. So that's the property of commensurability. Any 2 points can have their distance measured. So that's the property of commensurability. The next property is non-negativity. Of course, distances are never negative, right? If I talk about the distance from here to there, it's also the same thing as the distance from there to here, and both of these are positive numbers. Or if I'm at if I just say, a distance from here to here, that's kind of a weird thing, but we will call that a distance of 0. So the distance is 0 if and only if the 2 points are the same point, right? So the distance from A to A is 0. And if the distance is 0, then you're dealing with the same point. So that's non-negativity, that the distance must never be a negative number. Could be 0, but that's precisely the case where you're dealing with just 1 point. And the final property is symmetry. And I've already kind of said it, that I've written down symmetry over here, that the distance from A to B is the same as the distance from B to A, and that's like saying the distance from here to there is the same thing as the distance from there to here. So that's symmetry. Anything that has these properties we are willing to call a distance metric. Now, I will not ever again, probably, or at least not for a long time, actually write the distance function. I will instead write just AB to refer to the distance from A to B. That's a common notation in geometry, and it should be kept distinct from the line through AB. Now, this is different, of course, because it's infinite. It's infinitely long, so to speak, so that there's no way it could be the same thing as the distance from A to B. So those are different things. Something easy to confuse it with is the line segment A to B. Now, how is that different from the distance from A to B? Well, the distance is a number. This is a number. AB is a number. The line segment from A to B is not a number. It's a collection of points. It's a line segment. Its length is a number, and in fact its length is this number, AB, but it is itself a line segment. It could have an angle with another line segment. This number cannot. So that's how those two things are different, and we will get into some theorems in the next video.